is we're going to prove this statement. We're going to prove that if a number when squared equals 2, then that number is not rational. The way that we're going to do this is a proof by contradiction. So we're going to have it where basically we assume that C is rational, and then we're going to derive a contradiction. So assuming C is rational implies that C is equal to the division of two whole numbers. So let's call those two whole numbers A and B. Now, I'm assuming C is rational. It means, so we know that C squared, we know that when this number is squared, it equals 2. That's the hypothesis. We make the hypothesis true. We know that when this number is squared, we get 2. And now we're only assuming that C is a rational number, which means that we're assuming it can be written as the division of two whole numbers. And let's call those two whole numbers A and B. Okay, this is our assumption. Now, off of our assumption, if we assume that it's rational, we know, again, this fact is the definition of rational. A and B are whole numbers. And what we have now is that this form, this A over B, can only fall into a few cases. It can only fall into 4 cases because every single whole number is either even or not even. Every single whole number falls into that umbrella, and no whole number is both even and not even. Okay, now the word for not even is odd. So every single whole number is either even or odd. And a whole number cannot be both even and odd. So we have it where there's 4 cases. That this A over B, that they're both odd. We could have it where A is odd and B is even, A is even and B is odd, or they could both be even. These are all the 4, these are every single case for the division of two whole numbers must fall into one of these 4 cases. So if I have it that, again, assuming C is rational, then that means that C must have it where it's the division of two whole numbers where they're both odd. C must be the division of two whole numbers where one is odd, the other is even. C must be the division of two whole numbers where the other one is even and the other one's odd. Or it must be the case that C is the division of two whole numbers where they're both even. So one of these 4 cases must be true. But now I use the fact that I know that this number when squared, so let's start with this first case, which is an easy case. I know that when C is squared, I get 2. Now C, I said, if it's a rational number, there must be two whole numbers, A over B, and in this case I'm saying that they're both odd, that when squared must equal 2. This gives me A squared over B squared equals 2. And again, if this equation is true, then this one must be true. And if this one's true, then this one must be true. A squared equals 2 times B squared. This is just the chain of logic. Right? You have it where if C squared equals 2 and C is equal to A over B, then A over B squared must equal 2. And then this is just the definition of squared. A over B times A over B is A squared over B squared. And then if I multiply by B squared this equation, right? If this equation is true and I multiply by B squared, these cancel. B squared over B squared is 1. I'm left with A squared equals 2B squared. Now, if we investigate this equation here for this case, so in this case, the two whole numbers are both odd. So now you just need to sit here and look at the left-hand side of this equality. An odd number, so A is odd. An odd squared is odd. So the left-hand side is odd. But if you look at the right-hand side, an odd squared is odd. So it's 2 times some odd number. And then 2 times an odd number, you should convince yourself, is even. And I started out by saying that no number, right, this is equality between these two sides. So whatever number is over here has to be the same number over here. Now, again, a number cannot be both even and odd. So this cannot occur. And we know that if C is rational with A over B whole numbers, then they both can't be odd. okay, because of this contradiction. An odd cannot equal an even, because we know that, again, this number when squared gives me 2. And I could follow this chain down to here where I'd get an equation that cannot be solved. This is a whole number. I know it's odd. An odd number squared is always odd, so the left-hand side is odd. But then this is an odd squared times 2, which is even. And an even cannot equal an odd, so it doesn't matter how long you try. It doesn't matter how many attempts you make at trying to solve this equation where a and b are both odd, you will always fail. Now I go to the next case, and I do the same kind of argument. I already know, you're right, c squared. I run through the same equation. Okay, but now in this case, it's just that it's the same idea, but we just got to keep in mind that a is odd and b is even is this case. So you have it again where you have this a squared over b squared. I'm just wasting time here. A squared equals 2b squared. The same way I got it before. And again, if we look at this equation tells us everything. An odd squared, right? A is odd in this case. B is even, and an even times 2 is even. So again, I get the odd on this side, but an even on this side, which cannot occur. So this cannot occur. So case 2 now cannot occur. Now, case 3. Case 3 is a little bit more tricky because you think maybe at first when I go down and I'm going to run through this argument again and get the same equation, I'd get a squared equals 2b squared. That if I run through this argument again and I see, look, a is even. An even squared is even. And then 2 times an odd is for sure even. So even equals even. Oh, so this one can occur, and then therefore the c squared or c can be rational. It's not true. I only demonstrated that this left-hand side is even and this right-hand side is even. But that doesn't guarantee that these two things can ever be the same. And I can illustrate that they can never be the same. Okay, I can illustrate that they can never be the same. The way it is that I can illustrate that they can never be the same is convincing ourselves of 2 statements in this case. So the 2 statements you need to convince yourself of in this case is that an even squared is always a multiple of 4. Multiple of 4. And this here, b is odd, and odd squared is odd, times 2 is even, but this is an odd number times 2. So 2 times an odd number. This is the other statement. So this is one statement over here on the left-hand side. So this is one statement. An even squared is always a multiple of 4. And 2 times an odd is never a multiple of 4. Okay, and now what you have here is you have, okay, with these 2 facts you can guarantee. Now look, here's again, you have to have a basic understanding of the logic. The logic is that if I'm trying to show equality, right, among these 2, right, the left-hand side and the right-hand side, every single property that the left-hand side has must be had by the right-hand side. If 2 things are the same, whatever property the one thing has must have by the other. If I demonstrate a property that, if I find a property of object X that object Y does not have, then I know X does not equal Y. So in this left-hand side, I will show you, you can convince yourself that this is some even number. A is even in this case. And you can convince yourself, sit there and go, 2 squared, 4 squared, 6 squared, 8 squared, all the even numbers, as many as you like, you will guarantee that it's a multiple of 4. And then you can convince yourself that you can do 2 times any odd number, and you will see that it's never a multiple of 4. So the left-hand side has a property that the right-hand side does not. So the left-hand side is a multiple of 4, guaranteed. Whatever number A you choose, that as long as A is even, the left-hand side will be a multiple of 4. But it doesn't matter what you choose for B, as long as B is odd. 2 times that odd number squared will never be a multiple of 4. So the left-hand side is always a multiple of 4, is going to be a multiple of 4, while the right-hand side cannot be. And this eliminates case 3. And you could just write this out. Like, you could just make a little bit of an argument saying, like, look, an even squared is always a multiple of 4. 2 times an odd is never a multiple of 4. So case 3 cannot occur. Now, again, that's just an argument of multiple of 4. Now, the case 4 case, okay? What you have here is a tricky one, okay? You want to start off at the beginning. You want to realize that if I have it that A and B are both even to begin with, A over B, right, where they're both even, right, let's say that I find out that A over B squared equals 2, okay? What this implies is that then sum even over even squared equals 2. But if I find 2 even numbers that when I divide them and then square like this here gives me 2, then one of the other 3 cases must be true. So what I say is my statement is this: so let's write our statement. Let's make sure that it's clear, because if you write this out, then you're in good shape, because it illustrates you understand. Because let's write if A and B are both even with A over B squared equaling 2, if A and B are both even, then let's just say that if this case is true, if case 4 is true, then at least one of other cases must be true. Okay? And now, why is this statement true? Let's see why it's true. So if they're both even, A over B, let's say I find it out to being, I don't know, 1402 divided by 1,000. Right? I find out that this number, when squared, gives me 2. Okay? Well, I could always reduce this, because the top and bottom are both divisible by 2. So this would be, 701 over 500. And now, if this is true, then this for sure should be true. And it will reduce into one of the other 3 cases. And that's always true for any 2 even numbers. If they're both even, then I can reduce it, and one of the other 3 cases must be true. Now, it's easier to see this as long as you convince yourself of this statement in blue. If you convince yourself of this statement, then it's easiest to see how we're pretty much done. Because now you want to write the contrapositive of this statement. The contrapositive is if none of other cases true, then case 4 is not true. Okay, and that's the contrapositive of this. These two are completely implying one another. Case 4 is that they're both even, right? And again, if none of the other cases are true, then case 4 is not true. I showed that none of the other cases are true, therefore case 4 is not true. And I showed, under the assumption that C is rational, right, that then none of the cases for A over B, where A and B are whole numbers, can be true, which means that my assumption is wrong. My assumption is wrong. If my assumption is wrong, I assume that C was rational. This implies C is not rational. And that word is irrational, as some of you know. Not rational. And this is the argument. It requires everything. If you write out what I did here, that's pretty good, but you should also have the understanding. You should also be able to verbally back up everything that you write.